Okay, this is the last little lecture about waves. Just a couple of details that are hanging out there we haven't talked about. The first thing that we need to talk about are standing waves. And standing waves are a little bit of a misnomer, I guess. Standing wave is a series of waves that interfere with each other in such a way as to look like they are standing still. So we said that if you shook a pulse towards some sort of fixed barrier, that the barrier it would reflect in the opposite direction. So if you shook a pulse towards the barrier and just as it reflected back, you were to send another pulse, those two pulses would cross each other at the center and they would have destructive interference. And if you continued to shake at a specific frequency or period such that just as one wave got to the end, you shook another one, you would create waves that appeared to be standing still, but they had a dead spot in the center. So if this was the original location of the medium, that your wave would actually take on a look that looks like this. And then it would flip back and forth between the solid blue line and the dotted blue line. It would go flip, 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 flip like this. Now I'm drawing a solid thing on the other side because once you get this thing going, you don't need to continue flipping the rope. Its reflections will interfere with itself and create this pattern. This pattern looks like it's standing still. This is a standing wave. Now areas on the standing wave that aren't moving at all are called nodes. So there's a node there, there's a node there, and there's a node there. Areas on a standing wave that look like they're moving a lot are called antinodes. Okay, so antinodes are the areas that are moving a lot. Now, what can we say about this standing wave? Well, the frequency and the period that you have to shake at to get this thing going is very specific, and it's based on the size of the area, the length between the two walls there. That length has to somehow match, and in this case, the wavelength of the wave is exactly equal to the length between the two walls. That's the standing wave that fits, but that's not the first or easiest standing wave. There's actually one easier standing wave that fits between the walls, and that is if you were to shake a wave that had only one antinode, a node at each end and one antinode in the middle. Now, what would be the relationship between the wavelength and the length for that one? Well, that's only half of a sine wave, so half of a wavelength is equal to the length between them. And of course, you could shake faster and get more waves to fit in the space between these two things. And so we could do what would be the next most complicated thing we could do? We have already got one antinode, two antinodes. How about three antinodes? Let's hit that. Now, three antinodes. We're going to have a node at each end, and then two. Oh, no. Yeah, exactly. So we got. I'm a little spastic there. All right, so that would be the next thing. Tell me, can you figure out what the relationship is between the wave's length and the length between the two walls? That's right. There are three halves, 1.5 wavelengths between the two walls. And these things where we compare the size of the wave to the length, and this is referred to in the business as boundary conditions. Okay. So, second thing I want to talk about today, and let's just put a line right here so we can use this paper a little more effectively. How to make the calculations. Well, first off, the easy calculations are having to do with frequency, which is the number of things that happen in a certain time, or calculating period, which is the time it takes for one thing or things to happen. And so let's imagine that you are a bird sitting on a power line. So here we got our two things, and there's a power line between them, and you're a little birdie bird, and you're sitting right here. Notice my birds look like the letter A. And let's just say that you're vibrating up and down, that you're going up and down because the wind is blowing and making this thing go up and down. And you go up and down 30 times in 1 minute. So, what are your period and frequency? Well, your frequency is going to be 30 cycles, 30 times in 1 minute, which is 60 seconds, which is a half of a hertz. Notice that I turned 1 minute into 60 seconds. And your period is going to be 60 seconds for 30 shakes, or a period of 2 seconds. That's as easy as those calculations are. Now, the other calculations using the wave equation are not quite as easy because they got one more ingredient. This is the wave equation. So let's now imagine that you're a surfer and you're taking a break. So you're outside of the break area. So let's just say that these are the waves that are starting to break here, and you're sitting on these waves over here. So you're on your little surfboard. I guess you're not standing, you're kind of sitting or laying, and you're going up and down, and you notice that you go up and down with a period of 12 seconds. Every 12 seconds you go up and down. And furthermore, you measure the distance between one crest and another to be, let's say, about 20 meters. That's about 60 feet between one crest and another. How fast are these waves really going? Well, we can use the wave equation. V equals lambda f, or lambda over t. In this case, because we know t, let's go lambda over t. And that's going to be a wavelength of 20 meters divided by a period of 12 seconds. And if I was smart, I would have made that 10 seconds, because now I need to use a calculator. 20 meters divided by 12 seconds equals 1.666. So 1.7, let's say. So those waves are going about 1.7 meters per second. 1.7 meters per second. And now you know why it takes a while for the waves from a storm to reach the coast. They're maybe not going that fast. Maybe twice walking speed, maybe jogging speed or something like that. Okay, so there's one more thing I wanted to talk about today. And by the way, just for giggles, this is the second time I've done this little lecture, because I hit record the first time and it didn't record. So I need to learn to look for the little red square. The next thing I wanted to talk about was wave speed. One thing I said is that a wave speed depends on the medium. So it doesn't matter, at least most of the time, it doesn't matter how large the amplitude of the waves are. Once you have a wave on a medium, it goes at a fixed speed depending on the medium. Now, tight ropes have much faster waves on them than more slack ropes. Thick substances sometimes transmit waves faster than thin substances because the molecules bump into each other more quickly. But there's another thing that affects it, and the type of wave. That is to say that transverse waves, that is where the medium moves up and down, but the disturbance, the wave itself, moves that way, may travel at a different speed than the same medium enjoying a longitudinal wave. And that's where the components of the medium are moving forwards and backwards, and the wave itself is going forwards and backwards. Now, as far as concrete examples of these waves, the transverse wave is what happens when you go to the baseball stadium and you get bored and you do the wave. Your body goes up and down, and the wave goes to the right or to the left, depending on which way the wave is going around the stadium. Longitudinal wave, it's a little harder to see how that is. You can get those going on a slinky. Is probably the easiest way to see those. Or I don't recommend it, but if you want to start a longitudinal wave in a line, if you're lined up to get lunch or something like that, just shove the person in front of you, and they'll bump into the person in front of them, et cetera, et cetera, et cetera, and you will create a longitudinal wave. The disturbance of the medium, the people, is forward and back, and the wave moves forward and back. Once again, I don't recommend that at all. But the interesting thing about this is that they can travel at different speeds. Now, when an earthquake happens, it turns out that both types of waves, both longitudinal waves, that is, pieces of the crust of the earth moving back and forth, and transverse waves, pieces of the crust moving side to side or up and down, are created. Now, the longitudinal waves are called P waves. I believe that's for primary, and the others are called S waves, which I believe is for secondary. But somebody also told me that P is for prompt and S is for slow. And the P waves and the S waves travel away from the epicenter at different speeds. The P waves tend to travel between, I guess it's about 5 to 8 kilometers per second, and the S waves travel from about 3 to 5 kilometers per second. The Earth's crust supports these waves, and they travel away from the epicenter. They get a little weaker the further you go, just because they're spreading out. Also, any dissipation in the Earth's crust absorbs energy, but the P waves arrive much more quickly, and so it turns out that the P waves, a lot of people report these as creating a shock, a very quick motion of the Earth, and that's the first thing you feel. And then, of course, the S waves are going to create a more rolling experience. And for those of us who've been through earthquakes, that is exactly what you feel when you are not right at the epicenter. You feel at first a jolt. It often wakes you up in the night, and then you start to feel this continued shaking of the earth that goes on for a while. This idea is what lets us find where earthquakes are in the United States. So I'm gonna quickly draw a really bad drawing of the United States here. Yeah, Texas is in the wrong spot, but you get the idea, right? So there's the United States, and let's just say that we have an earthquake here in, say, Arizona. So I'm going to put a letter E for epicenter. What happens is that there are seismic stations all over the place, and let's see, of course, there's one in Los Angeles. Let's say there's one up here in the Idaho, and then one over here. Okay, and these seismic stations receive the P waves and then the S waves. They have meters that can tell the difference between the P waves and the S waves, and the difference in arrival time tells them how far away from each station the waves originated. So the California station, the S waves are right behind the P waves, so they know, okay, this is only a couple hundred miles away. So they can draw a circle around the California station and say earthquake happened somewhere on this circle. Up here in the northwest, they get a bigger difference in arrival time, so they have to draw a bigger circle. And over here, they got a bigger difference in arrival time, so they have to draw a much bigger circle. And between this going on now, look, these two circles they intersect up here in Canada, but that doesn't match the California as well. So once you have three stations reporting, you can nail down the epicenter of an earthquake, and that's what they do. And they do it within a few minutes of an earthquake occurring. And then the gal from Caltech comes on TV, tells you how strong the earthquake was, preliminary magnitude. They have to wait till they can talk to the other stations and see if it makes sense to everybody involved. They can even tell you the depth below the Earth's surface. Some of these faults are, a mile below the Earth's surface, and they slip, and we can say, hey, it was under Lancaster, but it was about a half mile down, kind of thing. So that's how a difference in arrival time of waves can tell us a lot about earthquakes, because earthquakes generate waves in the Earth's crust. All right, that's it for the wave lectures. You should be able to finish the homework, and I expect to see a lot of people in office hours because the homework's due today.